right, welcome to one of our detailed lessons where we give you a proof. I think this proof is a nice one. It has a lot of little wrinkles in it. Then each of those wrinkles is a good reminder or contains something worth knowing. So I don't consider this proof optional. I don't expect you to memorize it, but all the little bits of reminders are things that are worth knowing. So we did a picture proof of the fact that the derivative of sine is cosine, and I'm going to use thetas today. And I want to prove it using an actual limit and the definition. So we're going to need a couple of things. First off, we're going to need to know what is the limit, out of h, I don't know where those h's came from, but of theta. And careful, I know those thetas look a little bit like zeros. Just a little reminder for you. This symbol is like a zero with a twist, or an O with a twist. This is a lowercase theta. It's a Greek letter. This function over here, sine of theta over theta, or sine of x over x, I would encourage you to go ahead and plot that, put it in your calculator, see what happens. There's a lot of ways of coming about this. We will have a real proof of what this is in a couple sections, and it'll go very fast. But if you zoom up to it, it kind of looks like this, whoosh, near 0. And that y value right there, go ahead and do it on your calculator if you haven't already, is a 1. The idea here, maybe a different way of thinking about this, is that sine theta near 0 looks one whole heck of a lot like x near 0. So at least nearby, they both seem to have a slope of 1, and they nearby is 0. They look kind of like that line, and so in the limit, they basically look the same. And so you end up getting a 1 out. And again, we'll prove this using something called L'Hopital's rule a bit later. I do want you to know this, actually. This fact ends up being more important than you might think at first. That the limit as theta goes to 0 of sine theta over theta is a 1. Almost as important, but it shows up a bit less, is this one, 1 minus cosine theta. And what is that one? Well, for similar reasons, right now graphing, but also L'Hopital's rule later, or you could kind of compare what the graphs look like near 0. This is actually going to be a 0. Today, actually, I believe the way this is going to show up is cosine theta minus 1. But if I do that, I'm just taking the negative of it, and it'd still be a 0. So these are pretty handy. The one on the left, definitely a bit more important. You can derive the one on the right from the one on the left, and vice versa. I need one more fun reminder, which is our angle sum formula. This only shows up every now and then for some reason, but when it does, it usually helps prove something big and important. So what happens if you have the sine of an angle plus another angle, a plus b, or the cosine of an angle plus an angle? And for some reason, one of my teachers in my past one time said to me, sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. And I still remember it to this day. Thanks, random teacher. But sine of a plus b is equal to sine of a cosine of b, cosine of a sine of b, and cosine of a plus b is cosine a cosine b minus sine a sine b. I'm not going to reprove that. Hopefully that showed up in your trigonometry or pre-calculus class. I'm going to leave it like that as a friendly reminder that we have these neat formulas. Things like this have been known for a very long time, even before trigonometry got super formalized. So, all right, all that said, we have only one tool right now for finding this derivative, and that is we have a definition. The definition for my derivative is going to be the limit as h goes to 0 of sine of theta plus h minus sine of theta over h. You could do this with x's if you want to, but it's good to mix it up. People often use thetas when they're dealing with angles. And that helps remind us that sine and cosine take an angle in and give a ratio out. But I'm kind of stuck now, right? Like, what do I do with this? Until I realize that in that first sine, I have the sum of two angles, which means I can use this angle sum formula. So let's go ahead and do that. Looks like I get, well, using that formula, sine theta cosine h plus cosine theta sine h, and then we keep this sine theta nearby, just from before. Nothing changes with that. Oh, okay. Well, maybe we can do something with this. All over h. What I want to do is split up this fraction into terms, and I'd like to sort of gather things. So let's just go ahead and look at, notice how this limit has an h, but we've got these thetas flying around. So in particular, I'm just going to focus on the terms that have a sine theta in them, and I'm going to gather those terms, hoping I can pull those out. So here I go. The sine theta is multiplying a cosine of h, and it's also multiplying a negative 1. And so I can rewrite those terms as sine of theta times cosine h minus 1 over 0. What's left is just this cosine theta plus sine of h, and I'm going to write that in a totally different limit because my limit law says I can. If I were to add these two fractions together, I should get this whole big original fraction. Okay, but I really just wanted to focus on this sine theta separately from this cosine theta. All right, so what now? Oh my gosh, this is starting to look mighty familiar, and this is starting to look mighty familiar. I wonder if you could finish this on your own. I wonder if you could go ahead and finish this off using those two fun facts up there. I bet you could. It's always better to try before I show you how. But I'm going to show you. I'm gonna take an extra step. I'm gonna go ahead, and my limit law says, hey, this is the limit with respect to h. H and theta are independent. They have nothing to do with each other. So I can even pull this out as a constant. Same with this cosine theta. I can pull it out as a constant just to make it really super clear what's happening here. And leave just my terms with h's inside. I left that minus 1 in there as well because I can't really pull that out from this h. Okay, now I hope it's really, really clear. What is going on here with this last term? Well, this thing right here, this whole limit right here is going to 0. This whole limit right here is going to 1. So what are we left with? This whole 0 term is going to go away. Sine theta times 0 is 0. Cosine theta times 1. All we're left with is just a cosine of theta. That is exactly what we wanted. Fantastic. Same game to find that the derivative of cosine theta is negative sine theta, but it's so repetitive that I'm not actually going to do it right now. So that was it. Nice proof that the derivative of sine is cosine, and worth going over because it also reminds you of, or actually maybe shows you these two neat facts that are worth knowing. This one in particular reminds you of your angle sum formula, and also reminds you of some of the games you can play with limits, especially if there's two different variables flying around. So very nice. And I think a lot of steps, but understandable. Okay, until next time.